Right now, 4 astronauts are further from Earth to prove that the spacecraft beneath them can keep humans alive in deep space. Because NASA needs that answer before it can do what it announced 10 days before this mission launched: build a permanent base on the surface of the Moon. So how does NASA actually build a city on the Moon? The city starts with nuclear reactors powering habitats through 2-week-long lunar nights. Pressurized rovers that astronauts live inside for days while crossing craters. Propulsive drones hopping 50 kilometers at a time to scout for buried water ice. A cell phone network on the lunar surface. And an end-to-end supply chain designed to keep 4 humans alive for a month at a time, 250,000 miles from Earth. This is NASA's 3-phase, $30 billion construction plan to build a permanent city at the Moon's South Pole. But to understand how we got here, you need to know what NASA just did. Because 10 days before Artemis 2 launched, NASA Administrator Jared Isaacman stood up at an event called Ignition and tore the entire Artemis program apart. The Lunar Gateway, the space station that was supposed to orbit the Moon, was cancelled. Every dollar, every kilogram of hardware earmarked for that station was redirected toward building a base on the surface instead. $20 billion over 7 years, $30 billion over the full decade. 3 phases, and a race against China that nobody at NASA will publicly admit. Phase 1 runs from 2026 through 2028. The objective is deceptively simple. Get to the Moon reliably. Get there often, and start learning what it actually takes to operate on the surface. NASA aims to complete 25 launches and 21 landings during this phase, delivering about 4,000 kilograms of material to the lunar South Pole. That includes 2 missions in 2026, along with delivery of 1 or both human landing systems being developed by SpaceX and Blue Origin. The Commercial Lunar Payload Services Program, known as CLPS, is being drastically expanded to support this cadence. But there is a reality check. Of the 4 CLPS missions attempted so far, only 1 has successfully landed and operated on the Moon. That was Firefly Aerospace's Blue Ghost Mission 1. Isaacman made it clear that contractors aiding this effort would have little room for error going forward. The Lunar Terrain Vehicle program has also been reimagined. The original plan called for a single rover built to survive 10 years, but the cost and timeline had ballooned beyond what the program could sustain. So NASA is deploying simpler vehicles first and upgrading them in later phases. The first 2 rovers are roughly the size of a golf cart, 1 crewed, 1 uncrewed. Each designed for a 1-year lifespan, capable of traveling at 10 kilometers per hour, climbing slopes of 10 degrees, and surviving up to 120 hours in shadowed regions. NASA's Viper rover is expected to arrive on Blue Origin's human landing system in 2027 to map water ice deposits at the lunar South Pole. That data is critical, because the entire base plan depends on knowing exactly where the water is. And alongside the rovers comes something NASA has never flown on the Moon before: drones. They are called MoonFall. Small propulsive hoppers built on the avionics legacy of Ingenuity, the helicopter that flew 72 times on Mars between 2021 and 2024. These drones survey terrain in hard-to-reach areas, making short hops that can cover up to 50 kilometers. They carry cameras and are designed to survive the frigid lunar night, which lasts about 2 Earth weeks. A first batch of 4 could launch in 2028, with more to follow in later phases. Their primary job is to scout the location of the future base. Another critical element of Phase 1 is the demonstration of radioisotope heating units. These are nuclear-powered devices that generate warmth to help rovers, drones, and other hardware survive extreme cold and long stretches of darkness on the lunar surface. 2 orbital constellations for communication and observation will also be deployed during this phase to lay the groundwork for astronauts to work collaboratively on the Moon in the future. And then there is the question of getting humans to the surface. Artemis 3 is now scheduled for 2027. Under the restructured program, this mission does not land on the Moon. Its goal is to fly in Earth orbit, dock with one or both lunar landing systems, and validate integrated operations. Life support, communications, propulsion systems, and potentially next-generation spacesuits will all be tested in the docked configuration. Artemis 3 will also be critical in testing the mission profile that NASA believes could enable semi-annual crewed landings starting in 2028. That profile involves multiple tanker flights to an orbital depot where the lander spacecraft fuels up before heading to the Moon. The data collected during Artemis 3 will directly shape the cadence and architecture of every mission that follows. If all of that works, the first crewed Moon landing since 1972 comes on Artemis 4 or V in 2028. NASA has also announced plans to collect data on a new Orion heat shield that will be installed for Artemis 3, addressing the issues discovered during Artemis 1. Both SpaceX and Blue Origin have fallen behind schedule on their lander development. NASA's Inspector General reported in March 2026 that SpaceX was about 2 years behind. Both companies face a list of complex engineering challenges, but NASA has said it will fly with whichever provider is ready first, rather than sticking to a predetermined order of mission assignments. Blue Origin's Blue Moon Mark 1 lander is designed as a single-launch cargo vehicle capable of delivering up to 3 metric tons anywhere on the lunar surface, using the 7-meter fairing of the New Glenn rocket. Its first flight will be a Pathfinder mission to prove out critical systems including the BE-7 engine, cryogenic fluid management, avionics, continuous downlink communications, and precision, landing within 100 meters of a target site. SpaceX has been conducting suborbital test flights of Starship since 2023. NASA officials indicated in March 2026 that SpaceX's version 3 Starship could make its debut in April 2026, with Blue Origin's first CLPS mission following a few months later. Both companies are also developing simplified mission profiles with less demanding surface requirements for the initial crewed landings. Their approach involves docking with the Orion capsule in a different orbit between Earth and the Moon than originally planned, before ferrying astronauts to the surface. The success of these profiles will be pivotal to the entire program. If all of this works, the first crewed Moon landing since 1972 comes on Artemis 4 or V in 2028. Phase 2 runs from 2029 through 2032. And this is where the South Pole stops being a landing zone and starts becoming a functioning outpost. NASA plans 27 launches and 24 landings during this phase, delivering approximately 60,000 kilograms to the lunar surface. That is 15 times the payload of Phase 1. To move that much material, NASA needs CLPS landers capable of carrying 5 metric tons on semi-annual missions. Power comes first. NASA plans to install solar masts that can power the base and wirelessly charge rovers. White House officials announced plans in 2025 for a lunar nuclear reactor by 2030. The combination of solar and nuclear power is expected to keep infrastructure running through the long lunar night, which lasts about 14 Earth days, and provide the electricity needed for research, construction, and daily operations. Communications come next. NASA will build a surface network with a line-of-sight range of 10 kilometers, allowing astronauts to communicate across craters and ridgelines using permanent relay towers. Think of it as the Moon's first cell network. Mobility expands significantly. In addition to upgraded terrain vehicles and more MoonFall drones, Phase 2 introduces JAXA's pressurized rover. Developed in partnership with the Japan Aerospace Exploration Agency, this vehicle is designed as a mobile habitat. 2 crew members can live and work inside it during surface expeditions. It travels at about 3.5 kilometers per hour, climbs slopes of up to 15 degrees, carries 3,000 kilograms of cargo, and can survive 150 hours in shadow. Unlike the Phase 1 rovers, it has a 10-year design life. Prototypes have already been tested near Flagstaff, Arizona. By this phase, lunar assets are expected to routinely use radioisotope thermoelectric generators, the more powerful successors to the heating units deployed earlier. These provide both warmth and electrical power, allowing hardware to function continuously through the lunar night. Perhaps most importantly, Phase 2 begins site preparation for the permanent base. Rovers capable of clearing rocks, leveling ground, compacting surfaces, and performing other construction-related tasks will be tested and deployed. These are second-generation terrain vehicles with larger payloads, working alongside machines contributed by industry and international partners. NASA's goal during Phase 2 is to support recurring astronaut operations on the surface. Regular logistics, 2 crewed missions per year. The beginning of a cadence that resembles what NASA has maintained on the International Space Station for more than 2 decades. The space station required 37 shuttle flights, 160 spacewalks, 2 decades of construction, and more than $100 billion to build. It has enabled over 4,000 research investigations by more than 5,000 researchers from 26 countries. The moon base is designed to eventually reach that same level of sustained human presence. To get there, NASA is drastically expanding its commercial lander infrastructure. On March 24th, the agency released 2 requests for task order proposals to the 14 CLPS Phase 1 providers, asking them to deliver large payloads up to 500 kilograms, as well as smaller science payloads under 100 kilograms. Launch Services task orders will be issued in 2027. A follow-on solicitation will look to expand the CLPS provider base beyond the original 14. The goal is not just more launches. It is a fundamentally higher rate of delivery to the lunar surface than anything attempted before. Phase 3 begins around 2033 and runs through at least 2036. It costs an additional $10 billion or more, and its goal is something that has never existed before in the history of our species: a permanent human presence on another world. During this phase, NASA plans to deliver approximately 150,000 kilograms to the moon. CLPS lander capacity increases to 8 metric tons. And the hardware that arrives is unlike anything that has come before. The centerpiece is the delivery of the first actual lunar habitats. Structures with environmental control and life support systems, airlocks, and all the features required for human occupancy over weeks or potentially months. They could span multiple locations. Italy's space agency is contributing multi-purpose habitats. Canada's space agency is providing a lunar utility vehicle. The habitats will receive power from the nuclear and solar systems installed during Phase 2, potentially allowing humans to venture into permanently shadowed craters for the first time. Alongside the habitats come 10-year rovers equipped with radioisotope power systems, capable of exploring shadowed regions with and without crew, transferring cargo, and digging into the lunar surface. To support increased human operations, NASA plans to build an end-to-end lunar supply chain capable of supporting 4-crew, 28-day missions. The agency hopes to return 500 kilograms of science samples and hardware to Earth at a time. The entire operation will be supported by satellite constellations and cameras providing live coverage of launches, landings, and surface operations as the base evolves. But Phase 3 is about more than living on the moon. It is about learning to live off the moon. NASA intends to create what it calls an industrial neighborhood, a zone where it can experiment with extracting oxygen, hydrogen, water, and rare earth elements from the lunar surface. It plans to test 3-dimensional printing using lunar regolith. Being able to produce those resources on site rather than launching them from Earth would dramatically reduce the cost and mass of future missions. And it would make something much farther away finally possible. This is the bridge to Mars. Every system tested on the lunar surface, every habitat module, every nuclear power unit, every water extraction experiment is a rehearsal for what humans will eventually need millions of kilometers from home. The Moon is close enough that a supply ship can arrive in days. Mars is not. If something breaks on Mars, you fix it with what you have. And the only way to learn how to do that is to practice somewhere closer first. NASA has said that the Moon base will serve as a proving ground for future Mars initiatives. The nuclear propulsion systems being developed for SR-1 Freedom are the same class of technology that could one day shorten the transit time to Mars. The life support systems being tested in lunar habitats are the same systems that would need to function for years aboard an interplanetary spacecraft. The in-situ resource utilization being prototyped on the lunar surface is exactly what a Mars crew would need to survive. The Moon is not the destination, it is the training ground. And Phase 3 is where that training begins in earnest. One of the most significant announcements from the ignition event had nothing to do with the Moon base directly. NASA revealed it will launch the first nuclear-powered interplanetary spacecraft before the end of 2028. It is called Space Reactor 1 Freedom, and it is going to Mars. This is not a radioisotope thermoelectric generator, the kind of nuclear battery that has powered spacecraft like the Voyager probes for decades using the heat of radioactive decay. Those devices are not propulsion systems. SR-1 Freedom is fundamentally different. It carries an onboard fission reactor. The thermal energy from the reactor generates electricity, which then powers highly efficient electric thrusters. This is nuclear electric propulsion. It works at any distance from the Sun, making it viable for missions far beyond Jupiter, where solar panels become useless. When SR-1 Freedom reaches Mars, it will deploy a payload called Skyfall. 3 small helicopters similar to Ingenuity, the rotorcraft, that became the first aircraft to fly on another world in 2021 and completed 72 flights before its mission ended in January 2024. But unlike Ingenuity, which was a technology demonstration, the Skyfall helicopters have specific jobs. They carry cameras and ground-penetrating radar to scout potential landing sites for future human missions. They will map and characterize subsurface water ice deposits, measuring their size, depth, and other properties. If the mission goes according to plan, it launches in December 2028 and arrives at Mars about a year later. And NASA may decide to keep flying SR-1 Freedom even deeper into the solar system after deploying the helicopters. This spacecraft is not just a mission. It is a proof of concept for everything that follows. SR-1 Freedom is designed to establish flight heritage for nuclear hardware, set regulatory and launch precedent, and activate the industrial base for future fission power systems across propulsion, surface operations, and long-duration missions. In partnership with the US Department of Energy, NASA intends to unlock the capabilities required for sustained exploration beyond the Moon and eventual journeys to Mars and the outer solar system. Those same fission power systems will eventually keep the Moon base running. And one day, they may power the ships that carry humans to Mars. Now, all of that, every phase, every habitat, every rover, every drone, every nuclear reactor, depends on one thing: proof that the spacecraft can keep humans alive in deep space. And that proof came from a 10-day mission called Artemis 2. The mission was originally planned under a different name entirely. It was called Exploration Mission 2, and it was meant to support the Asteroid Redirect mission, a concept proposed in 2013 where a robotic spacecraft would capture a small asteroid, bring it into lunar orbit, and send astronauts to study it. That mission was cancelled in April 2017. The objectives were revised. An 8-day free return trajectory around the Moon was proposed instead. Another proposal that same year suggested using the flight to deliver the first element of the Lunar Gateway Station. That was shelved too. The mission was folded into a new program called Artemis. The Artemis II crew was formally announced on April 3, 2023 by then NASA Administrator Bill Nelson at a facility near Houston, Texas. That evening, the crew appeared at a college basketball championship game at nearby NRG Stadium. The crew was Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and mission specialist Jeremy Hansen from the Canadian Space Agency. On the mission's first day, Glover became the first person of color to travel beyond low Earth orbit. Koch became the first woman. Hansen became the first non-American citizen, and Wiseman became the oldest person to make the journey. Hansen and his backup, Jenny Gibbons, were both selected by the Canadian Space Agency as part of a 2020 treaty between the United States and Canada that facilitated Canadian participation in the Artemis program. It had been more than 53 years since Apollo 17. More than half a century since any human being had left the protective shell of low Earth orbit. The mission's objectives were comparable to those of Apollo 8, the first crewed lunar flight in 1968. But unlike Apollo 8, which entered lunar orbit, Artemis II flew a free return trajectory, more closely resembling the path taken by Apollo 13 inches 1970. Although Artemis II flew much farther from the Moon than Apollo 13 did, Apollo 13 came within 254 kilometers of the lunar surface. Artemis II's closest approach was about 6,500 kilometers, a little over 2 lunar diameters. Artemis II launched aboard NASA's Space Launch System rocket from Kennedy Space Center's Launch Complex 39B on April 1, 2026 at 6:35 inches the evening Eastern Time. The flight was fully automated unless intervention was required, which would likely have been to issue an abort command. Wiseman monitored the launch from the left seat. The solid rocket boosters delivered the majority of thrust for the first 2 minutes, separating at roughly 5,000 kilometers per hour at an altitude of about 48 kilometers. The core stage burned for approximately 8 minutes, placing Orion into a highly elliptical orbit with a high point nearly 5 times above the International Space Station. The interim cryogenic propulsion stage did not fire during the initial ascent. Right after main engine cutoff, Koch and Hansen unstrapped from their seats and began setting up essential life support systems. Water dispenser, firefighting masks, toilet systems. These were the same systems that had caused delays on the ground for months. Now they needed to function for real. All systems checked out. About 50 minutes after liftoff, the interim cryogenic propulsion stage fired to raise Orion's low point. At that new low point, a 15-minute burn pushed the next high point out to about 70,000 kilometers, establishing a roughly 23.5-hour high Earth orbit. That burn expended nearly all the remaining fuel in the upper stage. Glover then moved into the left seat and took primary control of Orion. He performed proximity operations with the spent upper stage, flying in close formation and evaluating how the spacecraft handled using the Cooper-Harper rating scale. After those tests, the upper stage fired its engines to enter a disposal orbit and deployed 5 rideshare CubeSats from international partners. Germany's Tachhiels, studying space conditions on electrical components for lunar vehicles. Argentina's Atenea, mapping the radiation environment. South Korea's K-RADCube, testing a dosimeter that mimics human tissue. Saudi Arabia's Space Weather CubeSat. And a 5th avionics unit. The crew converted the cabin from launch to spaceflight configuration. They set up exercise equipment. They ate their first meal. Their first sleep period was split into 2 4-hour blocks, interrupted by a European service module burn. After that burn, NASA managers reviewed the performance of every system aboard. Then, they authorized the translunar injection, 5 minutes and 49 seconds on the service module's main engine. That single burn placed Orion on a free return trajectory toward the Moon. The outbound journey took about 4 days. During that time, the crew monitored systems, gathered data on deep space effects on the human body, and performed trajectory correction burns. 2 experimental payloads focused on crew health. Avatar, a system designed to mimic individual astronaut organs and study their response to deep space conditions, was tested outside the International Space Station and the Van Allen radiation belts for the first time. Arca tracked sleep patterns, movement, and immune biomarkers using wearable monitors and saliva samples. The spacecraft also tested optical communications through the O20 system, sending data back at up to 260 megabits per second to ground stations in California and New Mexico. Orion swept around the far side of the Moon at a closest approach of about 6,500 kilometers from the surface. Some portions of the far side were seen up close by human eyes for the first time. The farthest distance from Earth reached approximately 406,800 kilometers, the greatest distance any human being had ever traveled from home. The spacecraft used the Moon's gravity to bend its trajectory back toward Earth. 4 more days, trajectory correction burns, and then the re-entry. Approximately 40,000 kilometers per hour, the fastest crewed re-entry ever attempted, no skip. A steeper angle, straight through the heat, splashdown in the Pacific Ocean off San Diego, recovery by the US Navy. Once safely removed from Orion, the astronauts were evaluated at a medical center, performed a simulated spacewalk, and completed an obstacle course to measure how quickly they could adjust to gravity after days in deep space. Data directly relevant to future lunar surface operations. 10 days, 4 people, a loop around the Moon and back. It proved the systems work. It proved the heat shield could bring a crew home, and it cleared the path for everything that comes next. But getting Artemis 2 off the ground was its own ordeal. And that story matters, because it reveals just how difficult every step of this program really is. The core stage was assembled at the Michoud Assembly Facility in New Orleans. 4 RS-25 engines were installed by September 2023. Then a leak was discovered in one engine's oxygen valve hydraulics. Engine E2063 had to be swapped for E2061. That replacement was not completed until April 2025. The fully outfitted core stage was delivered to Kennedy Space Center in July 2024, but investigations into Orion's life support system and unexpected heat shield erosion from the Artemis 1 mission delayed rocket stacking by more than 2 months. The heat shield issue was the serious one. After Artemis 1 flew in November 2022, engineers found that the Avacoat ablative material had cracked and broken away in places during re-entry, eroding more extensively than any pre-flight model had predicted. Temperatures inside the crew module had stayed within design limits, but the behavior of the heat shield was wrong. Close-up imagery was not publicly released until May 2024, when it appeared in a report by the NASA Office of Inspector General. NASA assembled an independent review team in April 2024 to assess the heat shield and the agency's plan for Artemis 2. The review concluded in December 2024. Rather than replace the heat shield, NASA elected to modify the re-entry trajectory for Artemis 2, flying a steeper descent angle to reduce time in the thermal environment that caused the damage. The publicly released version of the review team's report was heavily redacted, drawing criticism from some former engineers and astronauts who felt the agency was not being transparent enough about the risks. Others, after reviewing additional data, said their concerns had been addressed. NASA engineers determined that the erosion was caused by gases becoming trapped within the Avacoat material, leading to cracking and localized material loss. NASA stated that testing and analysis showed the capsule structure would remain intact even under scenarios involving more extensive damage than expected. In January 2026, Isaacman stated that he supported proceeding with Artemis II after reviewing the agency's analysis and meeting with engineers and outside experts. NASA confirmed that heat shield design changes addressing avcoat permeability were planned for Artemis III. Stacking began in November 2024 and was completed in October 2025. The rocket rolled out to the pad on January 18, 2026. Then, a wet dress rehearsal on February 2nd revealed a liquid hydrogen leak. A second rehearsal on February 19th succeeded. But 2 days later, a helium flow issue triggered a rollback to the vehicle assembly building. The mission slipped to April. On March 12th, after a flight readiness review, 7 launch windows were announced. The crew entered quarantine on March 18th. The rocket rolled out a second time on March 20th. During a pre-launch ceremony on March 27th, Christina Koch announced the winner of a global design challenge. Over 2,600 submissions from more than 50 countries. The winning design was Rise, by an 8-year-old named Lucas Ye from Mountain View, California, depicting the moon wearing the Earth as a baseball cap. NASA fabricated the mascot and tethered it inside the cabin as the mission's zero-gravity indicator. And on April 1st, 2026, at 6:35 and 12 seconds in the evening, Eastern Time, Artemis II left the ground. Every delay, every leak, every redesign. That is the cost of doing this right. And every mission after this one inherits the lessons learned on the pad and in flight. There is a reason all of this is happening with such urgency, and it has very little to do with pure science. China's space program has been building toward a crewed moon landing by 2030. Step by step, one element at a time, the China Manned Space Agency has assembled the pieces. A crew ship called Mengzhou, with capacity for up to 7 astronauts, a lunar lander called Lanyu, a heavy-lift Long March 10 rocket, 2 launches per mission, rendezvous and docking in lunar orbit. 2 astronauts descend to the surface while the cruise ship waits above. Mengzhou is designed to be reusable, with a replaceable heat shield and landings cushioned by airbags in China's western desert. Testing of Lanyue began in 2024. Mengzhou flew its first robotic test in 2026. A joint test mission is planned for 2028 or 2029. The first crew could reach the lunar surface a year after that. What makes the Chinese program different is the continuity. The effort is the product of Project 921, first backed in 1992. Each piece builds on the last. Shenzhou, 1 inch, 1999. The first crewed flight on Shenzhou, 5 inches, 2003. Space stations starting with the Tiangong series in 2011, regular crew rotations ever since, with Shenzhou 22 launching in November 2025. And in 2024, Chang'e 6 returned the first ever soil sample from the moon's far side. They started slowly, deliberately, with long breaks between missions, only recently picking up speed. The Chinese approach has drawn comparisons to what NASA's own administrator, Michael Griffin, proposed for the Constellation program back in 2005. A crewed ship on one rocket, a lander on another, assembly in lunar orbit. A crew capsule and a lunar lander together are too heavy for a single launch, so you split them across 2 rockets and build the mission in space. It is a straightforward architecture. And observers have noted that when China announces dates, it typically maintains them. Each capsule, each station module, each robotic lander is not an isolated mission. It is a component in a coordinated long-term strategy to create a sustained presence in space that delivers economic, geopolitical, and strategic returns. The Long March 10 rocket, as configured for lunar flight, stands 92.5 meters tall and generates thrust of 2,678 tons. For comparison, the SLS that launched Artemis 2 produces about 3,992 tons. The Chinese rocket is less powerful, but the architecture around it is designed to be efficient, reusable, and sustainable over decades. That is the difference. NASA builds missions. China builds systems. NASA's path has been the opposite. The Constellation program under President George W. Bush. Its cancellation under President Obama. The pivot to an asteroid mission. The return to the moon under Artemis during President Trump's first term. The slowdowns during the Biden years. The Planetary Society estimates NASA has spent approximately $107 billion in inflation-adjusted terms on return to the moon plans through 2026. Much of that was consumed by program changes across successive administrations. Isaacman avoids using the word China directly in public. He speaks instead of a great rival, a competitor moving at impressive speed. But the urgency behind the ignition announcements is unmistakable. He told NASA employees that the clock is running in what he called a great power competition, and that if the agency falls behind or makes a mistake, it may never catch up. He warned that the consequences could shift the balance of power on Earth. Whether that framing is justified or strategic, the effect is the same. It is giving Artemis a sense of urgency that the program has never had before. Some NASA veterans say China may be doing for Artemis what the Soviet Union did for Apollo, giving the agency a reason to move faster than bureaucracy normally allows. So here is where things stand. Artemis 2 has flown. The hardware works. The heat shield held. The life support systems functioned. For the first time in over half a century, humans have traveled beyond low Earth orbit. Artemis 3 is planned for 2027, a docking test in Earth orbit with one or both lunar landing systems. If that succeeds, the first crewed landing comes in 2028 on Artemis 4 or V. After that, NASA targets landings every 6 months with at least 2 launch providers. Commercial rockets gradually replacing the government-operated SLS. The moon base begins with rovers and drones and small payloads at the South Pole. It grows into solar masts and communications towers and pressurized rovers that serve as mobile habitats. It becomes a cluster of habitats powered by nuclear reactors, connected by a surface network, serviced by a supply chain that can return samples and hardware to Earth. Beyond the moon, the Nancy Grace Roman Space Telescope is set to launch as soon as this fall, advancing our understanding of dark energy. Dragonfly, a nuclear-powered octocopter, launches in 2028, arriving at Saturn's moon Titan in 2034. NASA will deliver the European Space Agency's Rosalind Franklin rover to Mars in 2028 with an instrument that may enable the most advanced detection of organic matter ever conducted on the Martian surface. A new Earth science mission launching next year will measure the evolution of convective storm dynamics, potentially improving extreme weather prediction up to 6 hours before events occur. The JWST continues to transform our understanding of the early universe. The Parker Solar Probe has flown through the atmosphere of the Sunday. NASA has demonstrated planetary defense by deflecting an asteroid. On the International Space Station, groundbreaking experiments in quantum science are underway. With an accelerated CLPS cadence, NASA is targeting up to 30 robotic landings starting in 2027, with payload opportunities open to industry, academia, and international partners. Students and researchers across the country are being invited to put instruments on the lunar surface for the first time. The moon base will not appear overnight. It will be built through dozens of missions across a decade by a coalition of space agencies, commercial companies, and researchers. It will cost tens of billions of dollars. It will face setbacks and delays and failures that nobody can predict. Only one of 4 commercial lunar landers has successfully operated on the Moon so far. Both crewed lander providers are behind schedule. The heat shield still needs a redesign. Congress still needs to approve the shift from Gateway to a surface base. There are real obstacles between where we are now and where NASA says it wants to be. But for the first time, the plan is not abstract. It is phased. It is funded. And the first pieces are already moving. Somewhere out there, 250,000 miles away, the south pole of the Moon sits in permanent shadow. Ice hides beneath the regolith. Craters hold temperatures colder than anything found on the surface of Pluto. And in those frozen, lightless basins, there may be water, oxygen, and hydrogen. The raw materials not just for survival on the Moon, but for a supply chain that reaches all the way to Mars. We have been staring at the Moon for as long as we have been human. We went there once, briefly, and then we turned away for half a century. Now, we are going back. And this time, the stated goal is not to visit, it is to stay. Whether we actually pull that off remains to be seen. The history of this program is littered with plans that never survived contact with budgets, politics, and the sheer difficulty of what is being attempted. But the rockets are being built. The rovers are being designed, the drones are being tested, the nuclear spacecraft is in development, and the Moon, as it has for 4.5 billion years, keeps turning. Waiting to see what we do next. What we know so far is that the plan exists. The money is allocated. The first missions are on the manifest. What the data suggests is that the hardware works well enough to proceed, even if it is not yet perfect. Some researchers believe the timeline is achievable. Others argue that the history of this program gives plenty of reason for skepticism. What if the landers are not ready in time? What if the commercial providers cannot meet the cadence? What if the political will shifts again? Those are fair questions, and nobody at NASA pretends to have all the answers. But there is a difference between this moment and every other moment in the last 50 years. The rockets are not on paper, they are on the pad. The crew is not hypothetical, they have flown. The plan is not a promise made to a future Congress. It is a set of contracts, solicitations, and hardware orders already in motion. And somewhere in the permanent shadow of a crater at the south pole of the Moon, ice waits beneath the dust, as it has for billions of years, until someone comes to dig it out.